Hello. I rather like coming down here because I was actually born in Sandringham, just not too far away from here, and grew up in Eltham. I went to Melbourne Uni. Yes, definitely from Melbourne, although I've been living in the UK for 15 years now. It's trying to tell me. I've been working with investment banks and hedge funds for about the last 9 years in the UK, and also quite active on Stack Overflow, and I have a gold badge for quite a few technologies, including Java and JVM. And in fact, I have the most answers for Java and JVM, about 12,000. So keep me busy. Yeah, about nearly 1.5% of all answers. I've also developed a piece of software branded Chronicle software. It's designed to be low latency and high performance, largely used in trading, compliance and risk systems in fintech, which is why I'm based in London, because most of my other clients are in New York and Chicago. So we have a number of open source products, which you can read, of course. So if you're interested in what does low latency Java code look like, you may find this library interesting. It is a pure Java implementation for accessing off-heap memory, native memory, shared memory, persisted shared memory. And it supports, well, it says 64-bit, it's really it's assigned 63-bit sizes. And we've got users using Q, which are accessing 100 terabytes plus in a single JVM by using memory map files. Also, they're using map, which is to about 10 terabytes, which is a key value store. Again, that's within a single JVM. Because they're shared memory, any number of JVMs on the same machine can be sharing that memory. So there's only actually one copy, and they're all seeing each other's copy, which means that messages can be passed between JVMs in around as low as 0.1 microseconds, which is fairly short. That's because it's not using TCP, and in fact, it's not even using any system calls, because system calls, even just the simplest system call, takes around 2 microseconds. So this is my first computer. I first had this in Eltham, and it had 128 kilobytes of memory, and it went at a whole 5 megahertz, whereas the IBM PCs at the time went at 4.77 megahertz. And so it was faster. But probably the coolest feature was that it had a full color VGA screen, which at the time was really nice because it could do graphics. It also had 1 megabyte floppies, which again was huge for those days. The point I was trying to make from this diagram, though, is that out of that 128 kilobytes, because I was programming machine code, I never used it all. I never found a use for all 128 kilobytes. So where do microservices come from, which is the topic? That microservices come from the Unix principle, which is do a simple task, do it well, make it reusable. Don't try and do too much in any one individual service. Technology architecture design which sort of built around this was stage event-driven architecture, which was largely academic. Not many people use this, but it was a precursor to service-oriented architecture, which is much more widely used. And in fact, a lot of people see microservices really just being a rebranding of service-oriented architecture. The fundamental difference, though, with microservices is because microservices is very much coming out of the DevOps world, they're much more concerned with independently deployable services. So whereas microservice-oriented architecture quite often is deployed as a single release of everything consistent versions across all your services. Whereas microservices are designed, every service can be released completely independently, has its own schema, its own data sets, that you can upgrade any one of them without having to alter any of your other services, which is one of the fundamental differences there. Lambda architecture, which is something that I advocate to the basics of Lambda architecture because it is such a simple architecture. And reactive streams, which is getting more and more interest. In particular, Oracle are looking to announce their sort of next generation replacement of Java EE. And it will be around the cloud, it'll be around microservices, and it'll be around reactive systems. So they're some of the key things they're looking to advocate at Java 1. Okay, so where did microservices come from? Originally it was called micro web services. It's very much coming out of the web space, which gives it a lot of strengths in the sense that a lot of it is easy to use, it's mass application, it's accessible to end users and to developers. But one of the things that is a sort of a time constraint is that your timings are based around what is perceptible to a human. So so most movies, until quite recently, were all 24 frames a second, which is around 40 milliseconds. And about 40 milliseconds, and some people give higher numbers, sometimes hundreds of milliseconds, maybe even 500 milliseconds. But at 40 milliseconds, you're at the threshold at which a human can't tell a difference. So anything faster than 40 milliseconds, a lot of people in the sort of that have come out of the more web space say, well, those delays don't matter because you can't tell them anyway. Like a human just could not tell a difference. And that has a lot of merit, but it means that a lot of these solutions have been designed with that sort of constraint in mind. So a lot of REST architectures say, well, if it only takes a few milliseconds, you can't see that anyway, why worry? So what has tended to happen is as capabilities of technology has improved, as bandwidths have gone up, as computers have got faster, instead of web pages loading faster, they actually take about the same amount of time to load, but you can put in richer functionality. And one of the impacts of this is that the average web page has gone up, and according to this website, the average web page has reached the point where it's around the same size as the game Doom. So about 2.4 megabytes was the size of the original game Doom, and that's the average size of a web page. So web pages are getting richer, not faster, which makes sense because that's more appealing to end users. Microservices denial. So one of the things that I come across, particularly in banks, is that they say, well, web services are a buzzword and we don't do buzzwords here, so we're not particularly interested in them. But the reality is that actually microservices is not something terribly new. It is really about trying to bring together a suite of best practices that work together. And in reality, a lot of companies are already doing a certain amount of best practices already, many of them which are compatible with microservices. So the interesting thing is that the discussion tends to go around between conflicting views. First, they say, well, it sounds like marketing hype. We wouldn't do anything like that here. So sort of initial reaction. Then they say, well, actually, it seems to be what we've been doing all along, which is, of course, the opposite. Then they say, well, actually, we could call a lot of our stuff microservices just by rebranding it. And so actually, they don't need to change anything. Just give it cooler new names. But where you actually start to see, well, what is the point of all this? Is there a point to even doing this? Is that you start to see there's a gap between what you're doing currently and what is considered best practice in a number of areas. And if that area is a pain point for you, that gives you an opportunity to change the way you're doing whatever that technique is to meet with best practice. And finally, you may decide that rather than just improving what you've got, that there is a tool that's tasked with a particular purpose, whether it be orchestration, whether it be serialization, or whatever this is a problem for you, you can just replace it with a tool that's been designed for microservices. So this is a spreadsheet I went through with a client. We identified a number of different techniques that are relevant to microservices that they thought were important to them. And in many cases, until we got to about here, they were already doing something around that area. So they didn't need to change anything terribly fundamentally, at least initially, just to be able to say, well, we're using microservices and we're looking to improve. And in fact, when we looked at where there might be quick wins, the biggest areas of improvement were these last three, which were transparent messaging, so that you could see the messages as they were being passed around the system, which means that you can validate them in ways that would be difficult to test for. Working as independent teams, they'd grown organically quite rapidly, and they hadn't really thought about, well, if we've got so many teams looking at so many different areas, how do we get the business to scale so that we can get each of those teams working more independently and therefore more efficiently? And looking at using Lambda Architecture more, because as you'll see in a moment, Lambda Architecture is very simple. It has limited application because it is so simple, but where it can be used, it will improve the maintainability of your software. So, using microservices and trading systems. A lot of the areas where microservices are looking to branch into actually overlap with what trading systems have been doing in terms of distributed systems for quite some time. But there are benefits to applying microservices in trading systems, and that is because a lot of what has been done in fintech is usually ad hoc. It's usually done from scratch. There'll be some architectural decisions, you must use this or that technology, but from then on everything is done, all the techniques that are used, there's no mandated technique, there's no best practices really put down, because they tend to hire very smart people and they can figure it out for themselves. But that doesn't mean that if you use some of these techniques you wouldn't get your solutions delivered faster. And in particular, a lot of development teams don't focus so well on how easy is this software to maintain. Particularly in London, they use a lot of contractors. In fact, some banks use almost only contractors, that the entire team's a contractor, the team lead is a contractor, which means that as soon as the project's delivered, they're on to the next project. They're not going to be worrying about, well, how easy is this software to maintain? And in particular, if you have a piece of software and it is successful, it can cost 3 times as much to maintain as it did to develop in the first place. So long-term maintenance is something that you should be considering from the start. And one of the things that microservices does is to break things into easily managed and understood components, which means that now you can upgrade or replace that component without having to understand the entire system or change the entire system. And it also encourages simpler programming models because you're trying to build, it's more Lego-based development. And the flip side, what can microservices learn from trading systems, is that trading systems have been built as performant distributed systems for many years. And you can achieve levels of performance which I've heard argued again and again you can't do in microservices, when in reality trading systems have been doing this for years. And in particular, there's a real emphasis on asynchronous messaging, which is something that a lot of microservices are still grappling with. They're still, because they're coming from using REST, which is not really designed for asynchronous, they're starting to move across to WebSockets, which is something we support. and that's probably the best route into asynchronous messaging for a web application. But trading systems are usually built around asynchronous messaging, so right from the start. And you can see an improvement in performance of an order of magnitude on the same hardware. Particularly when you have a lot of simple tasks, because the overhead of dealing with each task becomes more dramatic when you have simple tasks. If you've got a small number of very expensive tasks, then the cost of your infrastructure, the cost of how you do messaging, these are no longer so important. But a lot of web applications are being broken down into smaller and smaller pieces of applications. Some applications are doing anywhere into the hundreds of operations to satisfy an entire web page. And if you add the overhead of each message, this can really accumulate. Another thing that trading systems are really designed to do is to have a high degree of determinism and auditability. You can build systems that do the same thing again and again. For the same input, you will always get the same output. And the reason that's so important is because, particularly in trading systems, is the cost of losing even one message can be very high. So, for example, in asset classes like FX or fixed income, exchanges or fixed income, bonds, the minimum trade size is $1 million or £1 million or €1 million. That's the smallest size. And often they don't get many trades of that size. They're usually larger. So you don't need to lose many of those for it to be a bad day, right? The money isn't lost. You can still trace it, but usually you have this long discussion with your manager and his manager and the business side's manager and so on, right? So, having complete auditability and determinism is an important feature. And built out of that, it means that you've got complete traceability of your system. So what is low latency? This is a term that gets used quite a bit, and it does mean different things in different contexts. I would say that the minimum for low latency is that you have a view as to what the latency of your application will impact your business. How will it impact your end users? You've got a figure in mind. It may not be real, maybe just an estimate or a hand-wavy gesture, but you have a view as to how much reducing latency will benefit your business. Sometimes I see people just say low latency. All that means is we care about latency, and maybe we even measure it. But I don't think that's that's just throwing out the term. I think you should actually have latencies you measure, and you have a view as to how important it is to your business that you achieve certain latencies. Now, in our case, where we, as I mentioned earlier, you can have latencies you can see, but certainly in the low latency systems I tend to work on, and there's a variety of those, they all care about latencies you can't see, right? So you can't use the normal tools, which is to actually just see whether it's slow or not, right? You need to write programs that measure themselves so you know whether they're running fast enough or not. So it's a different problem. And you want to know about how consistently are those programs measuring those sorts of latencies. So to give you an example, this is one of the more stringent requirements that a client had with us recently. The worst one in 100,000 was coming in at 450 microseconds. Now, usually clients don't even measure the worst one in 100,000 or even have a view on how bad that should be. But in this case, they did, and in fact, they wanted it to be under 35 microseconds, which took us quite some time to figure out, and we actually had to write some software to measure the program to work out where was it, and it was to do with a date-time conversion. So we've narrowed it down to a single line of code, which was causing that outlier. But there's an example of how strict it can be, and this is in Java, right? This is not in C or C++. This is in Java. So where do trading systems and microservices overlap? There's quite a number of areas. One of the areas of interest and a big challenge for companies like Oracle is the private data sets. Oracle, Hazelcast, Terracotta, they all advocate having a single world view of data which you can access from any application. But one of the things that microservices advocate is each service has its own data set, therefore its own schema, so that it can be upgraded completely independently without saying, well, you can't upgrade your service because there's another service also using those tables and they need to be upgraded as well, or even worse, in large organizations, we don't know who's using those tables, so we can't ever upgrade it because it's an impossible problem to solve. So one of the biggest challenges I see is actually these private data sets. How do data grids survive in a world where you're not sharing data between services anymore? One of the things that I advocate, which I don't think gets enough attention, partly because of the origins of web services, is transparent messaging. Now, one of the things that web services got right from the start is that you can read the contents of the messages. It was in HTML, they used XML, more recently JSON is used quite widely. At every point, a human can read those messages. They're not as easy to read as maybe they could be, but you can check them quite easily. Now, one of the challenges I think is the shift towards HTTP2, which is more of a binary protocol, and we've actually done a shift in the opposite direction. We started with a binary protocol and we shifted back to something that is transparent and human readable. And that's because you need another means of validating your input. And this is particularly useful when you have these separated services. When you have two services, a service talking to another service and they're not behaving correctly, which one is wrong? It's very easy to be able to go chop, right? Let's look at all the messages that are sent. Are the right messages being sent? Yes. If the right message is being sent, the producer is fine. It's the consumer that's doing it wrong. Are the wrong messages being sent? Well, okay. In that case, it's the producer's problem. You can divide and solve your problem very quickly. And in particular, when you have two teams working on these two services, being able to quickly identify which team is the source of the problem is very useful, because otherwise you're going to have teams blaming each other. If they can validate their own work against what messages should be sent, then you can solve a lot of problems and a lot of issues much quicker. So transparent messaging, I think, is very important, and this is one of the values that web services already have. Trading systems do this generally very badly. They have all sorts of protocols. Even if they're text, they're written in such a way that they're almost impossible to understand unless you've been reading these messages for a long time. A good example is the FIX protocol. FIX protocol is a financial exchange protocol. The first field is field number 8, right? It's a mandatory field. Second mandatory field is 9, of course. The third mandatory field is field 35, and everyone knows what 35 is, of course. The last mandatory field is 10. Sorry? There's a 42, and it's just randomly picked numbers that make no sense whatsoever. Some of them have to appear in a certain order, some of them don't. Some of them have codes for, like for example, buy and sell. It's a one-letter code. You'd think they use B and S or something like that. No, it's 0 and 1. Some places it's 1 and 2. Some places it's 0 and 2. Yeah, so it's text. But, oh yeah, and the separator is Control A, because comma or pipe, who knows? You know, let's use Control A. Nobody else does. Okay, so let's move on to Lambda architecture. So Lambda architecture is actually a lot more, I'm simplifying it here, but this is the bit that I find interesting, and this is the bit that's applicable to trading systems, is that you start with an ever-growing list of events. You have a write-only data structure. An example of this that we don't produce is called Kafka. But we have Chronicle Q, that's our alternative. And so you feed in events, and those events are only append only and continuous message. Then you have a function which does some sort of translation, and you get outcomes from that. It can be 0, 1, or multiple messages as a result. Now, as you can see, this is very easy to test standalone. The problem with it, of course, is that it's very simple. Not all problems fit into this space, and in reality, these tend to work best as translation tools. So, in particular, if you've got an external protocol, external message types, and you want to translate them into your model in your message types, or the reverse, you want to take your message types and send them to external message types, then this sort of thing works very well. What is actually a more useful one is a modification of the Lambda architecture, which is where instead of treating each individual event in isolation, you treat the input as every message that's ever been written. Now, of course, it would be very expensive to replay every message that's ever been written every time. So as an optimization, you can retain as state anything that's derived from the input. So it could be, for example, in an order management system, it would be all the latest orders. But you don't keep every order. You just keep what is your working set, what you need to remember to be able to process future messages. And then this becomes a component that's actually a lot more useful because it has state, it can build on things, it can do more complex things. And so you can chain them together. And I have actually built a very simple system that does this, this is pretty simple. But what tends to happen is to make this work, this becomes a very complex component. In reality, this becomes almost your monolith if you're not careful. So this is a monolith, and we've got these little translation tools input and out at the end. So it's not very well broken up, but if you've got a simple enough system, this can work quite well. Getting slightly more complicated, at least one of our clients works this way, where what they do is this is the critical path, this shortest bit, because you care about the latency of your critical path. Any message going through it should be going through it as efficiently as possible. And so any message that can't be dealt with immediately gets handed off to some asynchronous threads that do additional processing, or contact an additional resource such as a database, and then they feed in the results as input. Now this is an interesting property which solves one of the problems that a lot of banks have, is that you have no access to production in test. So you've got no way of reproducing any kind of problem in test that happened in production based on some state of the database. And even if you did, the database may have changed since then. So you still don't have access to what was the state at that moment. So instead, because these are ever-increasing recorded logs, which are replayable, in fact, they're always in replay mode when they're actually running a production, what happens here is this message says, I need to get, say, some additional information about a user, or I need to get some additional information about a security, and I don't have it. So this becomes a message out here. This strategy is listening to this, goes and executes the request against the database, and then feeds it as input. Now this becomes input in a queue. You've got total ordering of every message here. So you know exactly what you knew, when you knew it, and in what order you knew it. So you've got complete replayability, but this system doesn't actually need to be here to replay it in test. You don't actually need access to production. You don't need to be running any other components. You can just test this component completely in isolation using a canned copy of everything you knew when you knew it. And this gets more powerful when you have bigger and bigger systems, or you're testing the performance of a larger, more complex system. Because one of the problems you get is that to test a complex system end-to-end, you need to see, because anyone can have an impact on each other, you need to run up the whole system to see how it's going to behave. But with these, you can test them in isolation because you replay the state of each one completely independently. So you only need to test that one system, which means that you can probably test that system on your development machine. I've worked with some, at least one bank. They have a lot of services, but they can only test it with every one of them running, right? And when I worked there, I made the mistake of improving their build system, because when the build system didn't work so well and it took them a whole week to do a deployment, they only had 235 services globally. In fact, it was a global deployment. You had to run services in 3 regions around the world to see if anything worked at all. Now they have 1,700 services, right? JVMs, 1,700 JVMs running. And that's the minimum configuration to test anything, which is quite impressive. Yes. I can tell you some more stories about that bank when I come back. Okay, so how do microservices work? How do microservices, in particular privately held data, relate to how trading systems are designed? Well, in trading systems, you care about much shorter time frames. So you want to be running at top speed as soon as you get a request, very quickly. You have very short warm-up times. Some of the trading systems I've worked on, they want to, from the time a packet hits their network to the time it leaves, a response leaves their network, they want that to be in tens of microseconds. So 35 to 100 microseconds. They might want to be under 100 microseconds at least 90% of the time. The client that I was talking about before, their target is 50. And to do that, you don't have very much time to warm up the code, you don't have time to warm up the caches, so you want to have your data running in cache all the time. And to do that, you want to make use of all the caches you have. So you're dividing the work across your CPUs, making use of all the CPU caches your CPU socket has. So in terms of performance, your L1 caches take around 3 clock cycles, so about 1 nanosecond. Which sounds very quick, but you do a lot of them. L1 cache is around 10 cycles, and L3 is 40 to 70. Now, the difference here is a factor of 3. So if you're working in this cache instead of the primary cache, you can be up to 3 times slower. In reality, you don't see that. You might see only about 50% slower. And the difference between L1 and L3 cache is now about 10 to 20 times. Right? Now, it's actually a lot worse than that. It's actually worse by an order of magnitude. The reason is that your L1 to L2 cache is private to that core. But when you have an L3 cache, it's shared. So if you've got 20 cores, then if any one of the cores is hitting that L3 cache, it can be slowing down another one of your cores, trying to hit the L3 cache. So in fact, the cost of hitting L3 cache can be between 200 and 400 times more expensive than using an L1 cache, because you no longer have scalability. You no longer have independent running of all of your CPUs. You're not running them concurrently anymore because they're waiting on a contended resource. We don't want to hit L3 cache really much at all, less than 1% of all memory accesses, which is pretty stringent. So really, this is a bit of a problem in Java because you've got no control over your caches. You don't know what's in cache, what's not in cache, or any of that sort of thing. All you can really do, though, is to make your working set for your thread as small as possible. And also identify when the working set has become too large and think about, well, how can I split this across 2 threads? Not because of the amount of work involved, but because the amount of memory I can now access is larger because I've now got access to more caches. So how does this apply in a distributed system? This is what I've already said. Okay, so this is a more classical arrangement. This is a little bit contrived. You'll see why in a moment. You've got some upstream components that are feeding data in, so market data gateways. You've got some control system, some core routing logic, and then you've got, say, an order management system. Now you've got some offline tasks, the threads you can farm out longer running work to, and you might connect to them via a high-speed bus. Now, in the past, this might be an enterprise bus, might have some sort of broker, but if you want to do this in a low latency play, you're actually thinking about, well, how's this arranged on my CPU? So I've got here 4 cores across the top. This is my big L3 cache in the middle, another 4 cores down the bottom, and these little caches here are my L2 cache, and I think that's the L1 cache. So you can actually apply them. So I've got these services running in these cores, and you can actually allocate a thread to a core in Java. And then all of the local data for that service, for that cache, is sitting in your L1 and L2 cache. So now you've got your private data sets, which is one of the things that Microservices advocates. But the benefit here is for performance, not just for redeployability. And then you're using this as you're actually using your cache coherency, your L2 cache coherency, as your fast, high-speed bus. And so then you can pass messages between, with serialization, you can pass messages in a few hundred nanoseconds between threads. Testing and debugging microservices. Now, while I'm quite a fan of microservices, it has some limitations. One of them is around testing and debugging. Testing and debugging distributed systems are a bit of a nightmare. And as the code gets more complicated, it gets harder because you don't, it's very difficult to trace a message or a series of messages going through your system. So what can you do about it? One way is to think about it a little bit differently. And that is to say, well, a microservice is a business component. It's important to emphasize that it is a higher level component that it comes from a business requirement, something you potentially could explain to the business as to why it exists. It's not just like an adder or something so low level that it just doesn't make any sense. And then to turn that into a service, you need to add a transport with serialization, so that that component is now remotely accessible to other components. But it does also mean that this transport, hopefully this is standard and it works, so you know this is not something that's in question. All you need to do to test your service is to test the business component itself. So if you design your business component right, you can test them in isolation, you can test them working together in isolation without a transport, and then see that they work. And you'll find that testing and debugging them that way will solve 90% of your problems, and it will do it much, much easier than trying to always test your system as if it was distributed. So here's an example. We have two interfaces. This is a Lambda architecture where you have an input queue, input series of events, output series of events. To keep it simple, I have one event for in and one event out. So here's my data type. We have an abstract masterable class, which if you extend it, it implements hashcode toString equals. So you don't actually have to implement any more methods than that. So apart from the constructor. So I construct the object, and so the toString looks like this. So our favorite serialization format is YAML, because YAML was designed to be human readable. It also supports types explicitly, so this is a type declaration. So, and it's more concise than JSON. You don't have to put quotes everywhere unless they're needed, so quotes are optional. It also supports comments, which was something we use quite a lot. We do use comments, again, in debugging. So it can be handy for a producer to write out some information, which is for debugging purposes, which has no real impact on the consumer, but when you're trying to trace a problem, you can read the comments. You can say, well, why, not only what is the value, why did I get that value? What does that value even mean? If I'm sending a code 2, I can put in as a comment, what does code 2 mean? You'll note that because it's written as a serialization format, the toString of any object can be deserialized and used to recreate the original object. So we have this is the implementation of our interface. So it implements our listener interface that takes one method. We take a constructor, which is the output, sets where is our output interface going to go. And this is actually a stateful lambda because what it's doing is in many in some exchange, most exchanges, when they send a price, they will give you a bid price and an ask price. What is the best price that someone will buy at? What is the best price someone will sell at? However, some do not do that. They send that information separately. And because it's quite standard to process things using top of book, which is the best bit buy and sell price, you might want to write a combiner, which takes the most recent buy and the most recent sell price, puts them together, publishes that as a top of book. Also makes a very simple example. So we have a map here of all of the prices, the latest prices for each symbol, and all this does is it creates a new entry if the symbol doesn't exist. So it creates a new object, top of book price, computes if absent, so it'll always return a price object. Then what I do is I pass in the cited price and call a method that does all the real processing, which I'm hiding as an implementation detail. But it may or may not trigger a result. So if the price didn't actually change, in this case, it doesn't actually trigger a new event. So the important detail is an event came in, it called this method with all this data, and then this may or may not trigger another event going out to the listener. Now the interesting thing about this component is that I haven't used any annotations, I haven't used any framework, I've used a methodology. Now, the interesting thing about methodologies as a vendor is they're very hard to sell. There's no product for a methodology, there's no license for it. But, and this is why a lot of companies don't push methodologies. They'll give you a solution for a methodology, like a library that does dependency injection, when in fact you could just do dependency injection rather than use a library to do it. So this is about a methodology here. And as you can see, I haven't really used any library or framework to do this. But I'm about to use one which is, in this case, EasyMock. The reason for using EasyMock is it makes it very easy to record the events that you expect to happen. Then you create the object and you give it the listener for the events you want to, where you want them to go out. And then you feed in some data, some events. And then you check that you got all the events you expected to get. So this service has now been tested in isolation. It works just fine. All the business logic works right. I haven't tested like transport. Is this using REST? Is this using JMS? It doesn't matter at this point. This functionality doesn't change because I'm based on what protocol I'm using or how I serialize the objects. Now, where it gets interesting is when you have multiple services or components you want to test together. So this market data combiner is being fed into an order manager. So it has its input interface matches the output interface of the combiner. It has another interface, which is the messages it produces. And so this is building up a scenario. Now, the result of this scenario is just one event, which is an actual order going out. To feed things into this, I can feed events into the order manager directly, which is some order IDs. Then I feed in some price changes. Then I feed in another order ID, which is the one that actually triggers an order. And then verify I got all the events I expected. The nice thing about this is the very first time I wrote this, there was a bug to debug it. And that was in the handling of, I think, this event. And to find out what was going wrong, I just stepped into the code. I stepped into the combiner, and then I saw the event which triggered in the order manager, and I stepped into the order manager, and I could see what the problem was. It was triggering an event it shouldn't have done, and then I could step back out again. So I could step all the way through in a single thread, end to end, and show all the business logic worked. You're just using a debugger. So then the interesting question comes up after the fact, which is, what transport should I be using? Now, in many cases, this will be mandated to you. You'll be told you expect it to use particular transport. And in particular, it's because you need it to work with other components. You're providing a service to other components. Now, you might decide you actually want to support more than one transport for different reasons. But that's all an option for you because your business component doesn't change the way it works to suit which transport you're using. Now in our case, we have Chronicle Q, so that's the one I'm going to talk about because that's the one I know the most about. But I'm just trying to make the point that up to this point, it's all methodology, and it doesn't really matter which transport you use. You can still use this approach. So again, going back to the transparent messaging, when you call this message in Chronicle Q, what you get in Chronicle Q is, in fact, the entire contents, that data serialized, but in using YAML. It doesn't actually record the type here because this, in fact, is the only type it could be. So it assumes that the reader knows this, and it will deserialize it as the appropriate type. This is a comment, and the comment here is to say that this has actually been encoded in binary. So it's a literal binary translation of YAML. So we've got the human readability of YAML, but we've got the performance of binary. And that binary can be automatically converted into YAML as required. So you don't need any knowledge, because it's a self-describing message, you don't need any knowledge of the application to decode it as text. But you get the performance benefits of binary. So some of the interesting features of Chronicle Q. There are a lot of solutions out there. This is not the only solution, as I've mentioned already. This is not intending to be better than an existing solution. This is intended to be an alternative. So it has some properties which are different to other messaging solutions. So one of them is that it's brokerless. There are some brokerless solutions out there. All it needs is for the OS to be running. So that is a requirement. And we have some alternative solutions if you want to be resilient in the event of a failure of a machine. But all your applications can die at any point and you won't lose a message. It's designed for low latency, which means that 99% of the time it can pass messages between JVMs. And this is persisting every message, by the way. No messages are lost if you shut down either process at any point or both. So every message is persisted so it can be replayed, and you still get less than 10 microseconds 99% of the time. All the messages can be read generically without having to have a knowledge of the application, which means that you can make schema changes very easily because any message can be decoded even if you start adding or removing a field or changing a type of a field. And in particular, we use kernel. We avoid using the kernel as much as possible. So we have very little system calls because, as I mentioned, every system call adds up, and they cost between 2 and 50 microseconds, which might not sound like a lot, but that automatically puts it puts a limit on what kind of throughput you can get out of a single thread. The sort of throughput you can get out of a single thread is the inverse of that latency. So if you've got a 50 microsecond hit on each message, then you've already said, well, the maximum I can do is 20,000 a second, right? Just because of that one thing that you're doing. So yeah, you want to avoid doing that. So this is an actual dump of the test I showed you earlier, where we had, so the bit at the top is the header. So you can dump all the header and see all the storage information, but you've got the order ID here, the top of book price, and again, these just match the data that you fed in to the test. And interestingly enough, because it is memory map files, it allocates in lumps of memory. So in this case, it starts at 80 megabytes. So that's why there's a bit of space left at the end. So doing a write latency test with JMH, the typical latencies for this test, writing those kind of messages with serialization, by the way, is around 3 microseconds. The 99th percentile in this case was about 8.5, and the 4 nines is about 20. We see a blip after about there, which is, we think is to do with the operating system, and we're looking at ways of tuning that, and in particular upgrading the operating system to new versions of Linux to help solve that. So another, as I was mentioning, Chronicle Q is looking to solve a different kind of problem. And in particular, one of them is to avoid flow control. So a fundamental feature of most messaging systems is that they have flow control. That means the consumer, if it can't keep up, can push back on the producer and say, hey, I can't keep up. Now, for a GUI application, this makes a lot of sense. This is a very natural thing to do. There's no point pushing to a GUI more data than either the machine can keep up, and certainly the human can't keep up. So that's completely pointless. Only send to the computer that the user is looking at that stuff that they can interpret. Because if you send them too much data, it actually stresses them out. So we've seen that with traders. If you have numbers changing too quickly, they actually prefer to see it moving slower, even if it's sort of momentarily less accurate. So they prefer to just smooth it out. So in a lot of messaging solutions, they're done on this basis where you want to have a minimum of flow control. You want to have flow control so you can push back on the producer. However, there are certain use cases where this isn't an option or is not desirable. And in particular, market data, you cannot tell the exchange to slow down if you can't keep up, right? They won't. They'll just kick you off. Simple as that, and you'll lose data. And in fact, one of the use cases for this is actually in Chicago. As Opera feed, they get peaks of 30 million events a second. They want to persist every event, and it's all sent via UDP. There's no retransmits, right? If you miss that UDP packet, tough. You missed the message, right? So it's quite an engineering challenge to say, well, I want to consume this and I want to record it and persist it without either losing messages because the network buffers fill up very quickly. So those network cards have only got a few megabytes, and once they fill up, they will start dropping packets. So you need to be able to pull data off the network card as fast as possible. And so market data is a good example of where you really don't want any kind of pushback. Another one is compliance, because certainly in Europe and in America, there's more and more demand for regulation for compliance systems. And they're often being added to existing systems, which means that the existing systems don't want to hear, well, you have to feed us data, but we might slow you down sometimes. They don't want to hear that. Whereas if you've got a system where you can send them data and it won't slow them down, they're much happier with that. So they like having this big buffer where they can just push data to, right, I have to send you this data. It doesn't really help me, but it just has to be done. So I don't want you to tell me to slow down. Coming back to microservices again, in a bit more detail. Microservices doesn't mean that it's not revolution. It's not revolutionary. It's not a major change. It's more evolution. It's really about attempting to bring in a set of best practices which may not be appropriate to your application. So to some degree, it is something that you can pick and choose. You can say these things are most relevant to us. These things are not so important. You will be doing some of these best practices already. A lot of people, some of the organizations I've worked at, they felt a bit stale. The techniques that they've been working on, they haven't changed for a while. Am I de-skilling here? But in reality, by rebranding them and pointing out, well, actually, these things are in hot demand right now. They've just got a different name now. But really, all those skills are applicable. Trading systems are engineered as distributed systems, even if they're all on one machine, because you're distributing work between the CPUs. And sometimes this is done very discreetly. Depends on the use case, but certainly in the more high-performance systems, it is passing messages. They know exactly which core a message is going to be worked on and which core that message is going to go to as a result. Lambda architecture is simple, sometimes too simple, but if you can use it, I strongly advocate farming out work into Lambda architecture components is a good way to start with microservices because they are very simple, they're a good use case. You can't pull out all of the functionality in your monolith or your distributed systems. You just won't do everything because it is so simple, but where you can use it, I think it's a big advantage. Where can I try this? I've put some examples together on this repo, and all of our open source stuff is available here. It's all Apache too, by the way. So, and last but not least, I have got a new blog and a website. So, yeah, have a look. So, time for questions? How long?
As long as you can stand, you want to be
That might be a good idea. Yes?
Yeah, that performance issue that you had to fix and get it down to under 35 microseconds. Was there any off-the-shelf profiling tools that you could use that granular?
No. And in fact, the question is, what sort of profiling tools do we use for the getting down that, that rare latency event? And the thing is that most profiling tools, they're useful as a first pass, and we use them a lot, partly to get just a different view of the application. So even if you're not so worried about performance, the performance is good, you'd be surprised how many bugs you can find in a profiler, not just performance issues. A few of the organizations I've been to, one of the top objects being created was exception. Right? And this is an exception that was being swallowed and going through a workaround. It just shouldn't have been happening. It was a bug. But it wasn't showing up in any of their tests. But it showed up in a profiler because it was one of the top objects being created. That's happened more than once. So profilers are useful to get as a view, but they're only useful as a first pass. And that's because they record averages. Right? So they will tell you where your latency has been lost on average or typically been average. But for the high percentiles, they won't show you that at all. But to see that, you really need to improve your typical first. To get the outliers, you need to have more detailed application-specific information. And we have a tool to do that. You don't have to use the tool. It's open source anyway. But we have a tool to do that called Java Latency Benchmark Harness. And it allows you to put timing points in your components. And they can be distributed across threads, although they have to be on the same JVM. We have techniques for using it across multiple JVMs and multiple machines, even getting nano-timings across machines. So that's one of the things we do. And by doing that, you can see where are my biggest hops in terms of latency. Doesn't tell you, it's still quite coarse, but what you can do is you can move around where you do the timing point. And this is where the reproducibility really helps. You take a few million messages, you replay them, you find that this portion is my biggest hit. When it's running slow, it's in this region. So you add a timing point, or you move the timing points around, and in our case, we narrowed it down to a single line of code by just adjusting the time. It takes a bit of time, but you can do it. Yes.
What are other profiling tools that you use?
Okay, so the main one I used to go to YourKit as my first preference, but more recently I've been using Mission Control. Mission Control, Flight Recorder. I find that's pretty good. One of the features I like about Flight Recorder, which isn't very well advertised, is that most profilers, what they do is they take snapshots at save points. Now, save point notionally can occur between any bytecode instruction, but what a save point does is it does a check to see whether that thread should be stopped. It's actually a memory barrier checked. And this is used for things like GC. So when a stop the world GC has to happen, it sets a flag. Every thread then gets to a save point and then stops. And once all the threads have stopped, you can now do any stop the world operations, like code replacement, but more often GCs. Now, of course, doing this check all the time is expensive. So what the JIT does is it tries to remove these save points. So it'll only put save points every so often. Sometimes it'll try and put it outside a loop, for example. So nothing in the loop has a save point. An example of this is copy memory, unsaved copy memory. What it does is it has no save points in it, which has the interesting feature that you can't have a stop world collection while it's copying memory. So you give it a big enough block of memory to copy, it will actually prevent the GC from occurring for that entire operation. Anyway, so the significance of save points is that that is the only points at which the thread can be stopped so that you can get a stack trace. So if you say get stack trace for another thread, you can do this at any point. You can ask the thread, give me your stack trace. But that'll only ever be at a save point, right? And of course, the JIT wants to reduce the number of save points to that is not continuously checking this memory barrier, which is an overhead on every operation. So there's a limited number of save points. The problem with that is that your profiler will only ever blame a save point, right? So the JIT has gone through and tried to remove a lot of these save points. They will never get blamed because you can't take a snapshot at that point, right? And because it can't take a snapshot, your profile kind of lies to you a bit. And most profilers have this problem, except for mission control, which cheats a little bit. It has a mode where it can take snapshots between save points. So you will get much more accurately what is the line of code that's causing the problem. So one example I had this was, there was one program I was working on, and the 5th biggest cause of CPU was integer hash code. Now, integer hash code, all it does is return the value. So it does nothing. It should be inlined. It shouldn't even exist, right? But it was the 5th biggest hit, and that's because that was the first save point after something that was quite expensive. So it was being blamed. So this is where sometimes profilers can lie to you because they're doing their best to blame the right things, but they don't always get it right. Even mission control has one problem that it actually, in its probes, and a lot of profilers have this problem, is that in their probes, they actually create garbage in doing so. And in Visual VM, one of its biggest problems is it creates garbage just running. So if you create a program, it's just system.in.read. That's all it does. It just sits there waiting for you to hit the enter key. So it's not doing anything. It is every thread, it only has one thread, main, and it's stopped, right? You connect to it with Visual VM and you'll see it sawtoothing, right? And you go, oh, what's it doing? Well, you enable the memory profile and like, oh, it goes really crazy then. And all the garbage is the Visual VM, JMX calls. That's not usually a problem because usually your application produces so much garbage that it's trivial by comparison. But in our case, we're trying to produce less than 1 byte of garbage per message. And so we have extraordinarily low garbage rates. So this is how we solve the GC pause problem. We just don't have GC pauses, right? So we avoid GC pauses by creating and having exceptionally low garbage rate, which means that when we run a lot of these profilers, the biggest garbage causes are the profilers themselves. It's not the application. So, so what you can do in your kit and in mission control is you can turn off these probes, then they don't produce as much garbage. But so there's some tweaks to get these things to work, but yeah, the main one I use is mission control because it has this nice feature where you can turn on profiling between save points, and because its allocator is actually quite good as well. It's recording of allocations. In particular, it's good for being able to see what a thread pool is doing. I haven't seen any tools that really, so you can just select the threads in a thread pool and say, what is this thread pool doing on aggregate? Your kit, for example, will tell you what any individual thread's doing, but say you've got a thread pool of 10 or 20, you sort of have to sort of sum it in your head. It's just much easier to be able to just select all the threads in a thread pool and say, what are these doing on aggregate? So I find that pretty handy. Mission control is that it has some animations. And animations run very badly on a high latency connection. So one of the things I do, which I think is perhaps not everyone does, is I run all the tests remotely on Linux servers. So I have a Linux server at home, and I can access it via X Windows from here. And it's pretty slow and laggy, but it can do it. If I use VNC, it's actually a bit better. But if you run mission control over even a non-trivial latency, say New York to Chicago, which is about 8 milliseconds, it can take minutes to do its animations. Right, 5 minutes or more just to bring up that opening screen and animation. You think, Why? Why can't I turn this off? It's a performance tool. Yes. Sorry. Yeah.
Thanks, great presentation. I've got 2 questions.
Sure.
What language is Chronicle Q written in?
At the moment, it's only written in Java. However, some of the Java will be sort of written in ways that you would not expect Java to ever be written in. Some of the things we do are, so some of the code, if you go into bytes, for example, we actually use memory addresses directly. And some of the use of unsafe gets turned into single machine code instructions. So we're doing some very low-level accesses, but we wrap that up so that by the time you're using outside bytes, you don't need to worry too much about all the low-level details. That's all hidden away from you. One of the things we do have is for remote access, we have a C# client, because some people do like to use C# or .NET or Excel, and having integration with the .NET solution is much easier under Windows. But most of the body of code is all in Java. Java 8, by the way, as well.
And my other question was, in your visualization of the CPUs and the processors, they're using all the cores.
Mm-hmm.
Do you not advocate keeping the CPU free for the OS?
Yeah, I actually advocate using dual socket servers. So yeah, keep an entire socket for the OS and all your junk CPUs. Then you get a minimum disturbance in your L3 cache. So then your L3 cache is effectively dedicated to your application. Is the reason for that. But yes, yeah, you have to really, because what you'll find is that if you ever assign a performance critical thread to CPU 0, which tends to be used by the OS a lot, more than any other, you will get a very poor profile. You never want to use CPU 0. Yes.
Regarding that slide and the CPU optimizations, isn't that potentially specific to the architecture of the CPU itself? Does that get thrown out as the CPU changes the way they handle their cache or even the abstraction of the Java?
You'd be surprised that the CPU architectures don't vary as much as you might think, even to the point that ARM CPU sizes are the same. So if you take it from the cheapest Atom mobile up to the top end Xeon, the size of the size and geometry of the L1 and L2 caches are the same. And the reason they do that is that there's certain C program algorithms that have been optimized for that exact specification, and if they were to change it, that code would run slower. So it's kind of like a backward compatibility thing, but for hardware. Sorry? Yeah, so AMD, sometimes they'll describe it differently. Sometimes they'll say they've got 64 kilobytes of L1 cache, but really they mean 32 data, 32 instructions. Sometimes they'll say 2 megabytes, but really what they meant is they have, well, not 2 megabytes. They might say a megabyte, but really what they mean is they've got 16 cores, and out of that 16, each one's got 64, and there's still the same amount of size. So different vendors will describe it differently, but in fact the geometry, the number of cache lines, the size of the cache line is always 64 bytes, even with ARM. And again, it's because on ARM you'll be running the same C code that was written for x86. And so that there's sort of a large disincentive. What they will tend to do is, instead of changing the size of the cache, is they might make it faster. So the number of clock cycles can vary. But then often what happens is the clock cycles don't really vary, the gigahertz varies more often. So they really don't play with those sizes or how the caches work very much. Except more recently, actually. Sorry, I'll come back to that.
You were talking about having several JVMs on one machine.
Yes.
What do you do if one machine dies? Like, how do you share the data between machines?
Yeah. So what we do is we have replication. So we have a couple of replication modes, asynchronous replication, and also we support synchronous replication. So they've got 2 ways of doing synchronous replication. You can either have the writer wait until it has been acknowledged by a second machine, or you can make it that the reader only sees messages that were acknowledged by a second machine, so you're not blocking the writer. So you decide But there's a number of strategies for doing that. There's another mode. What we used to advocate before we had that facility is that you have server A replicates to server B, and server B does the processing. So server B can't do the processing until server A has got a copy. The main benefit of that is you're not round tripping. And in many of these systems, every network hop really adds a lot to the latency. So if you can save a network hop, you can really cut down. So the sort of hardware they're working on, the network hops are around 10 microseconds. And even then, they want to cut out every hop they can. So that's another alternative. But in any case, you have two machines. You might have three. So say, for example, you really want redundancy to another data center, which is a long way away. But you don't want to pay the whole penalty. So what you'll do is you have two machines that might be in neighboring buildings or opposite sides of the data center. You get very good latencies between them, but you've got the possibility you might lose the data center. And if that happens, you lose a few messages that would have been also copied to the more remote destination. And some banks also replicate between regions. So they might replicate from London to New York, but the message time is about 35 microseconds. So you can lose, 35 milliseconds. So you can lose, you have that window where you could lose some data. But to lose an entire data center in a region would be quite a serious event anyway. Although Delta did that recently. They lost 2 data centers, which is impressive. That hasn't happened since September 11th, where there was a bank who had their DR site was in the second tower.
Not as high flying, but logging seems to be good, particularly for in your situation for replayability and so forth. How do you do that without affecting your latency?
Right, so what we do is we record, because we're recording everything in a reproducible manner, there's very little to log in addition to that. There's still things you want to log, like critical errors, things you can't possibly predict as a catch-all, failure to start up, for example, before this is even running. But in general, you're actually recording every input and every output. And at that point, you have complete reproducibility of the state and any information you might need to know about the system. So you don't need to log anything extra. And the other thing is, because you've got transparency of exactly what it's doing at every point, you may find that actually you start to say, well, some of the things it's doing, it doesn't need to do. And so one of our trading systems, the client was getting 35 microseconds end-to-end latency before they were use Chronicle Q. After they put in Chronicle Q, it dropped to 23 microseconds. So by using a technique like this, you can actually save time. They saved in 2 ways. One is that they weren't passing objects around. Because they're passing serialized streams, you're minimizing the amount of traffic that goes from one CPU to another. One of the problems with Java, as opposed to, say, C++, is that every object reference is an object that could be random in memory, which means a lot of cache misses, depending on how complex your object is. In C++, you can arrange your objects so they're all continuous in memory. You don't have quite that problem. And because we're serializing, you copy that data to continuously in memory, you're streaming continuously, you minimize the number of cache misses that are occurring. But more importantly, in their case, going back to the transparency message, they could actually see that some of the messages they were doing didn't need to be done, and therefore saved work, saved fields that didn't really need to be copied round. So instead of, because you're copying the message, you only copy the fields that are relevant, not all the ones that you might happen to have in your data structure. And by doing that, they cut down the amount of traffic going on as well. So I know it seems counterintuitive, but you can actually speed up your application by recording everything, which of course most people don't do because of the performance hit.
It's not log, it's sprintf. You're
That's correct.
Saving a set of memory in a parallel thread or something?
You're continuously writing in the current thread. So you're continuously copying to memory.
Oh, so it's part of your shared memory solution?
It's part of the shared memory solution. So the actual file format is you have a length at the start, a 4-byte length, followed by the contents of the message. That message could be your own string, it could be a byte array, or it could be one of the serialized objects, depending on how you want to do it. You can even get access to the address and just treat it as raw memory using JNI or Unsci. So you have access to all the different levels. We provide a high-level facade where you just treat as method calls, and then you get the same method calls called on your consumer. So that's the highest level interface. But and in all cases, it's just writing the data straight out serially to a stream of a file.
You're talking about 35 microseconds of performance. How functionally rich is the application? So what's it doing?
Very little. That's because going back to this diagram, all the functionally rich stuff is done up here, asynchronously. So it's not part of the critical path. All you want in here is your trigger points, right? So when an event comes in, you want to do in advance, work out what are all the scenarios that are likely to happen? And if this happens, what will I do? So you build up a table of trigger points. You say, if the price goes over this, I'm going to place an order. Or if the price goes under that, I'm going to cancel an order. So you just have a series of trigger points which you spend a lot of time thinking about. These are happening between events. So you actually have a lot of time between one event and another to make another fairly complex decision. So you build up a table of things that you want to do when it happens. And so when an event comes in, it can fire off very quickly. And in fact, you may actually have different levels. So you might have strategies which are slower, say an order of magnitude slower than your control system. And then you might have even slower strategies which are to do with risk management. And then you might have some which actually go to a human to check, right, which take orders of magnitudes longer. Right, so you can have actually stages getting further and further away from your core system. But you're right, to get 35 microseconds, you can't do very much in terms of code. You can still do a surprising amount, though. 35 microseconds is still 100,000 clock cycles.
So, for example, like your market data cleansing, so without being in the control system, would it be before or?
That would be in the normalizer. So by the time it comes here, it's a clean, standardized message. It's not enriched. You can't really, unless it's pre-programmed data. But if there's any kind of more complex enrichment, that might actually have to go off to a database to get some additional information. So again, this is only what you can do very simply as a translation. Often it's no more than taking an external format, which isn't actually very friendly, and making it a more friendly internal format. In Fix, you have dates as strings. You might not want to keep treating them as strings. You might want them as a date object, for example, or a long. So that's a very simple translation. In some cases, it's more complex. There might be an external code for a particular kind of client. You want to turn it into an enum. So a lot of these translations are very simple, but they reduce the complexity of your internal code. You're not polluting your internal system with details from a provider of data. So one of our clients, for example, they have 22 providers, and they all do things a little bit differently. They don't want this internal system to have to worry about all the little details of how all those providers do things a bit differently. They want a standardized message by the time it hits their more internal systems. Yes?
So you're describing this flow. What happens if any state changes? Doesn't that slow up the process?
Mm-hmm. So you can have a state change in here, and this is remembered in memory. But that state can be reproduced at any point from the input. It might be persisted to speed up restart, but it might not. It depends on your requirements. So you could recreate this state by just replaying every message coming back in again, or you might want to have it continuously persisted in, say, a persisted key value store, and that way you can just restart the process from any point, not have to replay all the messages from the start of the day or the beginning of time or whatever. Sorry. Yes, that was...
In order to read messages at such a low latency, do you use spin locking, or what sort of CPU usage is the thread at when it's not reading any
Right. So in a load, it depends on. There's a whole range, a whole spectrum. So of use cases, some people are quite happy with milliseconds. Some people, happy with 100 microseconds. Some people want hundreds of microseconds, tens of microseconds. So in the tens of microseconds range, you don't want to give up the CPU ever, because your caches will go cold. Right. So if you give up the CPU, that cache could even be powered down. So that means that when you come back up again, it has to be warmed up. That warm-up might take you 100 microseconds. Usually at 100 microseconds, your code runs a bit slow. That hardly matters. But in this case, that's your entire task. So every task is now running 2 to 5 times slower if you've given up the CPU. So you don't ever want to give up the CPU. You'd rather busy wait. You don't even want to make a system call if you can help it, because your caches will go cold, the data won't be as warm, and your code won't run as fast when you come back to actually doing some useful work. Also, you might slow down the CPU, so you want to run the CPU at maximum frequency all the time. So, yeah?
Sorry. We might just wrap it up now, sorry. So
Mm-hmm.
if we have any questions, maybe we can meet up afterwards.
Okay.
Would everyone just like to give a quick thanks to the beautiful presenter?